Genevieve speaking. In this presentation, we'll go over how to run analysis of variance using Microsoft Excel. We'll first address analysis of variance for completely randomized designs. Within that section of our presentation, we'll go over the Fisher least significant procedure, and we amend that with a Bonferroni adjustment. Next, we'll address analysis of variance for randomized block design, and finally analysis of variance for factorial experiment. So first, analysis of variance for completely randomized design. This is referred to as single factor ANOVA in Microsoft Excel, and we'll expand that in our presentation. First, we need to clarify that we are calling those analysis of variance, but what we're doing is running tests about population means based on analysis of variance. So we're comparing population means. The idea is if the means of the population are equal, we would expect the sample means to be close together. In other words, if the variability among the sample means or variance of the sample means is small, then it supports our null hypothesis that the population mean are equal. If it is large, then it supports our alternative hypothesis. That's it. That's the logic behind the analysis of variance to test population means. So for that, we'll use two estimates of the variance of the sample mean. The first one is the between treatments or mean square due to treatments measure. It's a good estimate of the variance of the sample means when H0 is true. It's not a good estimate of the variance of the sample means when H0 is false. It overestimates it. MSE, or mean square due to error, is the other estimate of the variance we will use. It also is called pooled or within treatments estimate. And this one is always a good estimate of the variance of the sample means, whether H0 is true or not. So this means the ratio of those two estimates will be close to 1 when H0 is true. In this case, SSTR and MSE are about the same, both giving a good estimate of the variance of the sample means. And this ratio will be large if H0 is false. And the ratio of those two variance estimates follow an F distribution with k minus 1 degrees of freedom in the numerator and nt minus k degrees of freedom in the denominator. K is the number of populations, and t is the total number of observations in our data set. So what we have is a standard and our familiar test statistics, where we can determine via the p-value approach or the critical value approach whether or not we want to reject our null hypothesis. Here we're looking at exercise 1 from chapter 13 in our text. A random sample of size 6 has been selected from each population or treatment. We have 3 population or treatments, A, B, and C. Total number of observations is 6 plus 6 plus 6, 18, which we can also obtain by multiplying nj by k, so 6 times 3, 18, since we have the same sample size for each treatment. The overall mean is simply the average of all the data, and we set our level of significance at 5.05, and this is how we organize the rest of our worksheet. SS stands for sum of squares, specifically sum of squared deviations of the sample means from the overall sample mean. MS stands for mean square, specifically mean of the squared deviations of the sample means from the overall sample mean. So mean squares are the measures of variance we were talking about earlier, MSTR and MSE, mean square due to treatment and mean square due to error. Both are computed by dividing the sum of square by their degrees of freedom. So next we look at how to compute those. So starting with SSTR, sum of square due to treatments. Looking at the equation, we are looking at computing the sum of weighted squared deviations of sample means from the overall mean. So cross treatments or between treatments estimate. So let's have a closer look at this equation. We always read an equation from the inside out. This equation is telling us to first take the sample mean from treatment J, subtract from that the overall sample mean. So that's the deviation of the sample mean j from the overall sample mean, squared, so that the squared deviation of the sample mean j from the overall sample mean, multiply it by nj, which is the size of the sample from treatment j, which means now we have a weighted squared deviation, so weighted by the sample size. Once we've done that for treatment j equal 1, compute it for the next treatment up to the last one, j equal k, or kth treatment. And finally, sigma, the summation sign, instructs us to add all the treatments' weighted squared deviations together. So SSTR does measure the sum of weighted squared deviations of the sample means from the overall mean. When we divide the sum of squares by the degrees of freedom, we do get an average of the squared deviations, or variance. So let's compute it. So following the instruction from the equation, so I'm going to take the sample mean from the first treatment, subtract from it the overall sample mean, then I want to square that, and actually you want to multiply that by the sample size. Okay, and then I'm going to do that for the next one. So sample size times the sample mean minus the overall sample mean, square that deviation, and next one and last one, sample mean minus overall mean, so that's my deviation, and square that deviation. Note that because we have equal sample sizes, nj is the same for all the treatments, so we can factorize that and multiply the sum of our squared deviations by n instead of each square deviation by nj. So we call it n now because it's a constant, meaning being equal across treatments. Here's how our equation is written in Excel when we do that. Degrees of freedom are k minus 1. Mean square due to treatment is sum of square divided by degree of freedom. So now to our next measure of variance, which is the average of the weighted sample variances. Given that each sample variance measures the variance within one treatment, it makes sense that mean square error is called within treatment's estimate of the variance. But since we also are taking the average of those sample variances, it's also called pooled. So again, we start by computing sum of square. So we want to make sure we understand how to read this equation. So it tells us to take treatment J sample variance, multiply it by nj minus 1. So nj is the treatment J sample size, which means that is the weighted sample variance for treatment J. And once we've done that for treatment J equal 1, we repeat that for the next treatment up to the last one, or kth treatment. Finally, we add all the treatments' weighted sample variances together. To get the mean square error, we divide sum of square error by degrees of freedom to give us the average of the weighted sample variances. So that's our second estimated variance. Let's compute it. So, equal sign. So we will get my sample size for the first treatment minus 1, close my parentheses, times my sample variance. And then I'm going to do that for my next treatment. Sample size -1 times the variance, sample variance, and -1 times sample variance. Here we go. So just like we had earlier, because we have an equal sample size, nj is the same for all treatments, we can factorize nj minus 1 and multiply n minus 1 by our sum of variances, sample variances instead. Here's our modified equation, looks like in Excel. Next, degrees of freedom nt minus k, mean square is sum of square divided by degrees of freedom. And finally our F statistics, ms due to treatment divided by ms due to error. We've worked with an F distribution before, back in chapter 11. So here, because the logic of our test is to reject a null hypothesis for large values of our test statistic, we're looking at upper tail test. So we use the f.dis.right tail Excel function to find our p-value, and the inverse equivalent to find our f critical values. No changes with the decision rules. If our p-value is less than our alpha level of significance, we reject a null hypothesis. And here with our upper tail test, if our F statistic is greater than our F critical value, we reject our null hypothesis. So the result of our analysis of variance, or ANOVA, is that we reject the hypothesis that the means for the three treatments are equal. And we can reuse this Excel worksheet as a template for future analysis of variance. Or alternatively, we can use Excel built-in ANOVA data analysis tools. So let's see how to do that. Select the data tab, then the data analysis tools. Select ANOVA single factor on the window that just popped up. You might have to scroll up to find the single factor ANOVA. Once you found it and selected it, select OK. Place your cursor in the input range window. Then with your cursor, select cells C2, E8. So this selection should include your columns, labels in the first row of the selection, and your data. You can just type the cell range in the input range window. Grouped by columns should be selected, because this is how our data was presented in our table. We check the labels in first row box to indicate that the input range we just specified did include our columns labels in the first row of our selection. We leave the alpha level at its default setting, 0.05, because that's the alpha level we chose. And then we specify a title for the new worksheet where Excel is going to display its computation of this analysis of variance, and we call it ANOVA single factor. Here's what we get. Those row labels are not quite fully visible, so let's do something about that. Select the Home tab, Format, Auto Column Width. Here we go. Now that column is wide enough, we can see those row labels. So if we compare the two, the table we constructed and the ANOVA table automatically generated by Excel, we can see that the built-in ANOVA analysis tool gives us the exact same result. We took the time to understand how to compute. We did add the interpretation or decision cells outlined here in yellow. So we rejected the null hypothesis that the means for the three treatments are equal. And we've established, so what we've established is that all three are not equal. But it could be that two of them are. So if we want to establish exactly which means are different, we need to run additional tests. So this is what we are doing next. For that, we are looking at exercise 14 from chapter 13 in our text. Here we've already done the analysis of variance and found that we reject the null hypothesis. So next we want to do pairwise comparisons of means so we can establish exactly which means are significantly different. We call that the Fisher LSD or least significant difference procedure. We've done hypothesis tests about two population means before, back in chapter 10. And we've established then that when the population standard deviations are unknown, our test statistics followed a t-distribution. We also pointed out that if the unknown population standard deviations are equal, which means if H0 is true, we're looking at one population and not two distinct ones. So then we can use the pooled sample variance as an estimate of our sampling distribution variance. So our t-statistics then becomes as shown here. In the context of our analysis of variance in chapter 13, mean square due to error is our pooled or within treatments estimate of variance. So then our t-statistics becomes as shown here. Using the critical value approach, we reject our null hypothesis if our t-statistic value, absolute value to be exact, is greater than our t-critical value. Replacing t by its full expression and rearranging our rejection rules becomes as shown here, which is the rejection rule found in our text. When we rename this product LSD, Fisher's least significant difference. So this term, that's the only thing new here. Renaming this term. We actually called this term margin of error before and used it to construct confidence intervals. Back to our Excel worksheet, we take the absolute value of the difference between the first two means. We compute our standard error, our critical t-value, and we can deduce the value of our LSD term. Finally, we are ready to use our critical value approach to decide whether or not to reject H0. So once we've done that for all three pairwise comparisons, we find a significant difference between population 1 and population 2 means, and population 2 and population 3 means, but not between population 1 and population 3 means. So now we might want to slightly adjust this procedure. So, excuse me, let's see why. We used alpha equal 0.5, so the probability of making a type 1 error with a single one of those pairwise comparisons is 5%. In other words, the probability of not making a type 1 error on each test is 95%. Now, what is the probability that in making three pairwise comparisons we'll commit a type 1 error on at least one of the three tests? Using what we've done back in chapter 4, we know that the probability that we would not make a type 1 error on any of the three tests is 0.95 times 0.95 times 0.95, which is 0.85. So the probability of making at least one type 1 error is 1 minus 0.85, which is 0.14. So when we use the Fisher LSD procedure to make all three pairwise comparisons, the type 1 error associated with it is actually 0.14, not 0.05. This error rate is referred to as the overall or experiment-wise type 1 error rate and is denoted alpha EW for experiment-wise. So if we want alpha EW to take on a specific value, not going over 0.05, for example, supposed to be as high as 0.14, then we'll need to restrict alpha to a much smaller value in the first place. This expression here on your screen now gives the exact level at which we would need to set what is referred to as comparison-wise type 1 error alpha. So at what level we need to set it alpha at to restrict our experiment-wise type 1 error alpha EW to a specific value. And this expression over here gives us the approximate level at which we will need to set our comparison-wise type 1 error alpha at to restrict our experiment-wise type 1 error to a specific value alpha EW. So this is referred to as the Bonferroni adjustment. So let's see how we would implement this. For the implementation, we're looking at exercise 14 from chapter 13 in our text. So we've done the analysis of variance and found that we reject the null hypothesis. So then we decided to do the pairwise comparisons of the means using the Fisher-LSD procedure. Here are the rest of them. So if we decide to use the Bonferroni adjustment, we simply decrease alpha before running our tests. We set the experiment-wise type 1 error alpha EW to the desired level, 0.05. So to get to that alpha 0.05, we need to set alpha, to get that desired level alpha EW 0.05, we need to get alpha equal to 0.008, much lower. So here with our algebraic expression, we can see that with 0.0083 times 6 pairwise comparison, we are indeed going to get to 0.05 for experiment-wise type 1 error that we were targeting. So all we did is recompute our critical t-value and LSD term with this new adjusted alpha value. Here are the rest of our pairwise comparison test using the adjustment. So this ends this section of our presentation on analysis of variance for completely randomized designs or analysis of variance for one factor. We now look at analysis of variance for randomized block design or two-factor analysis of variance without replication. So for that, we'll be working with exercise 21 in chapter 13 of our text. So at first glance, this looks very similar to exercise 1 we looked at earlier, with a data set for 3 treatments, A, B, and C. So what I've done is use the analysis of variance template we just constructed earlier for completely randomized designs and replace the data with the ones from exercise 21, which is going to end up being a randomized block design, like we will soon find out. So compared to exercise 1, we have 5 as opposed to 6 numbers listed per column, so number of observations per treatment. So in exercise 1, we had a random sample for each treatment. For example, each treatment might correspond to an industrial assembly method. So 3 assembly methods or treatments are of interest to us, and we'd like to determine whether the mean number of units assembled per week is the same for all 3 methods. So for that, we randomly assign workers to each type of assembly method and record for each the number of units assembled per week. So the method of assembly is our first factor. And now the question is, what if the number of units assembled per week not only depend on the method of assembly used, but also on the individual performing the task? So with the randomized block design, that's what we are going to try to establish. So instead of having different workers trying out different methods, we'll have the same random sample of individuals, and each individual from that random sample will be working with all 3 assembly methods. So this way we'll be able to measure the individual effect or block effect, that's the generic term we use here for this second factor. So this mean will be interested in computing the block means, just like we had computed the treatment means before. We call them treatment means now to distinguish them from the block means. The number of blocks used here, individuals, is the same across all treatments, so we change the notation to B without any J index, since B is constant. And we will compute a sum of squares and mean square due to blocks, as well as an F statistics due to test the block effect. When we were considering only the effect of one factor, the assembly method in our example, we used the sample variances to get our second measure of variance. This was our mean square due to error, because all the variations from the overall sample mean that wasn't explained by the treatments was deemed due to error. Now, with two factors, it's going to be easier to compute the sum of square due to error differently without using the sample variance. Total sum of squares, SST, is equal to sum of squares due to blocks, SSBL, plus sum of squares due to treatments, SSTR, plus sum of squares due to error, SSE. So now sum of squares due to error is whatever is not explained by the treatments or the blocks. So whatever is not explained by the assembly method or the individuals. And SST, sum of square, total sum of square, is simply the sum of the squared deviation of each value in our data set from the overall mean. So you can see that's easy to read now, right? That we have practiced with the other equations. This means we don't need these anymore, and we need to correct these. So let's get to that and the completion of the rest of our ANOVA table, where we first need to compute sum of squares due to blocks and sum of squares total. So this is our template that we are in the process of modifying and completing for our randomized block design. We already made the changes we just outlined. This is the equation we used for SSTR, sum of squares due to treatments, for the completely randomized design, or single factor ANOVA. In this context of a randomized block design, or two-factor ANOVA without replication, here's how it looks. We have B instead of N. Now we talk about the number of blocks instead of the number of observations per treatment. And now that we have an additional factor, individuals in addition to assembly methods, or blocks in addition to treatments, we need an additional index to keep track of our data. So we have this placeholder for an additional indexing of our averages, indicating here that we average the values for each treatment J across all blocks, or individuals in this example. To compute the sum of squares due to blocks, we proceed the exact same way. We weight our sum of squared deviations of the block means from the overall mean by the number of treatment K, so which corresponds to the number of observations per block. We also have a placeholder for an additional indexing of our averages, and this time indicating that we average the values for each block I across all treatments. We compute the sum of squares due to blocks, degrees of freedom or B minus 1, mean square due to block or MSB is sum of square divided by degrees of freedom. Next we compute the total sum of squares. So error sum of square is total sum of square minus sum of square due to blocks and sum of square due to treatments. Total degrees of freedom is total number of observation in a whole data set -1, and degrees of freedom for sum of square due to errors are degrees of freedom total minus degrees of freedom from sum of square due to blocks and degrees of freedom from sum of square due to treatments. So now that we have specified the degrees of freedom and the mean square due to error, as well as the F statistics and subsequent P and F critical values have been also computed, decision rules have also been applied, which means our division by 0 error messages have disappeared. We can compute the F statistics to test the block effect too, P and critical values, and apply the decision rules to both. So in this exercise, our main factor of interest was the treatment or assembly method. And the result of our analysis of variance is that we reject null hypothesis that the means of the 3 treatments are equal. So we can reuse this Excel worksheet that we just constructed or modified. So it has a template for future randomized block design or two-factor analysis of variance without replication. Alternatively, we can also use Excel built-in ANOVA data analysis tool. This time we select two-factor without replication. Note that the input range includes both the rows and columns label, and the data. So we check the labels box, leave alpha at 0.05, and name our worksheet ANOVA two factors, no replication. Here's what we get. If we compare the two, the table we constructed and the ANOVA table automatically generated by Excel, we can see that the results are the same. We did add the interpretation or decision cells, but they are hidden on this screen. So actually this ends the section of our presentation on analysis of variance for randomized designs or two-factor analysis of variance without replication. Last section, we now look at analysis of variance for factorial experiments or two-factor analysis of variance with replication. So for that, we're going to work with exercise 28 from chapter 13 of our text. And for now, what I've done is taken our template from our previous exercise and replaced the data with that from exercise 28. Compared to exercise 21, we have a total number of observations equal to 12 as opposed to 15. Most importantly, instead of having 4 different individuals, each working with all 3 assembly methods, we have only 2 different individuals, each working with all 3 assembly methods, but each over 2 different weeks. This means we have a mean or average number of units assembled for first individual and a mean number of units assembled for our second individual. So we don't have as many means for our first factor or factor A. This is how we refer to it now. This in turn means our sum of squares due to factor A, as well as mean squares, F statistics, and p-values are going to change. And since the sum of square due to error is computed by subtracting sum of square due to factor A from total sum of square, that's going to change too. And since mean square due to error is equal to the sum of square due to error divided by the degree of freedom, the mean square is also affected. And finally, since the F statistics for the treatment effect is equal to the mean square due to treatment divided by mean square due to error, it and its p-value are affected too. Now, we said we have only 2 different individuals, each working with all 3 assembly methods, but each over 2 different weeks. Over 2 different weeks means we have 2 repetitions or replications of the work via different assembly methods by our individuals. So in this example, we have 2 individuals and 2 repetitions per individual. If we had 2 individuals and 3 repetitions instead, this is how our table would look like. So those replications allow us to potentially detect an additional effect, which is the interaction effect. So in this example, the interaction of a specific individual and a specific assembly method on the number of units assembled per week. One more thing before we go on and compute this new source of variation due to interaction. We relabel our treatment factor and call it factor B. Here's our template that we are in the process of modifying and completing for our factorial experiment. So we already made the changes we just outlined. So first we enter the number of replications by hand. And then we can specify the number of levels for factor A to be the total number of rows of the data in our table divided by the number of replications. The total number of observations is then the number of levels for factor A times the number of levels for factor B times the number of replications. We modify the algebraic expression for sum squared due to factor A, since now with the replications we have only 2 factor A means as opposed to 4. The weighting of that sum of squared deviations of factor A means from the overall mean is now the number of levels for factor B times the number of repetitions. So 3 times 2, 6, which corresponds to the number of observations each factor A mean is based on. Once we've done modifying the algebraic expression for sum squared due to factor A, the number error messages disappear, but we still need to modify the algebraic expression for sum squared due to factor B and write down the one for the interaction effect before we get our final values for F statistics and P values. First, sum squared due to factor B. So similarly to what we had for factor A, the weighting of the sum of squared deviations of factor B means from the overall mean is the number of levels for factor A times the number of repetitions. So 2 times 2, 4, which corresponds to the number of observations each factor B mean is based on. Next, sum of squares due to interaction between factor A and factor B. First, we compute an average for each group of data characterized by a given level of factor A and a given level of factor B. So we outlined those groups here on the screen. We're looking at the deviation of each of those means from the overall mean. So that only comes from the interaction effect of factor A and factor B. Let me restate that we want to look at this deviation that only come from the interaction effect of factor A and factor B. So from each deviation, we subtract or factor out the deviation explained by factor A alone and the deviation explained by factor B alone. That's what we get. And after simplifying the algebraic expression and taking the square of it, and doing that for all groups characterized by a given level of factor A and a given level of factor B, adding them all up and weighting them by the number of repetitions, we get our sum of squares for interaction. Sum of squared deviations of the group means from the overall mean explained only by the interaction of factor A and factor B. Here the equation for the sum of squares for interaction is entered in Excel. This degrees of freedom for the interaction term is degrees of freedom for factor A times degrees of freedom for factor B. Mean square due to interaction is sum of squares divided by degrees of freedom. Error sum of square is total sum of square minus sum of square due to factor A minus sum of square due to factor B and minus sum of square due to interaction of factor A and factor B. Same thing for degrees of freedom. Finally, we compute the F statistics to test the interaction effect and the P and F critical values and apply the decision rules to both. So our final results are that factor A the individual one, and factor B, factor A, the individual, and factor B, the assembly method, are not significant each individually, but interaction between factor A and factor B has a significant effect on the mean number of units assembled per week. Here again, we can reuse this Excel worksheet as a template for factorial experiments or two-factor analysis of variance with replication. Alternatively, we can use Excel built-in ANOVA data analysis tool. This time we select two-factor with replication. The input range or range of cells we select includes the rows and column labels, specifically the names of the levels for factor A and factor B, and the data. The rows per sample is the same as the number of replications. We leave the alpha level of it at its default setting, 0.05. Specify a title for the new worksheet where Excel will display its computation of the analysis of variance. Here we call it ANOVA two factors with replication. Here's what we get. If you compare the two, the table we constructed and the ANOVA table automatically generated by Excel, you can see that the results are the same. We did add the interpretation or decision cells, and again here they're hidden on this screen. And that's it. I guess this ends the section on analysis of variance for factorial experiment or two-factor analysis of variance with the replication. And this also concludes our presentation on analysis of variance.